Hey everyone, I want to talk today about some advanced validation techniques. And this is stuff that maybe I should have showed you earlier, but since this is the first time I taught the class, I wasn't really sure when or even if to introduce these topics. Um, but after seeing how we did in the breast cancer homework, I thought, I saw a lot of overfitting going on, and I thought that this was probably time to address this topic. Okay, so this is a surprise, but this is important stuff, so let's cover it. All right, I have a data set here, and the data set is from a sport. This sport is called billiards, and billiards is a highly competitive sport. It's similar to bowling, but it requires players to strike a set of inflatable bumpers before their ball strikes the pin. And how billiards works isn't really all that important. But what is important is how we build a model to predict who's going to win a game of billiards. All right, so we're going to read our data in. I'm going to look at this data. You can see that there's some stuff in it like player number and then some variables that we know about the particular player, like maybe their shoe size and the games they've won this season and last seasons and the times they faced a particular opponent and things like that. Anyway, you get the idea. You can download this and look at this at your leisure. Um, we know that this unnamed zero is like an index and this player number. They're not useful, so I'm going to drop those. I'm going to pull off the dependent variable, which is win, and that's what we want to predict. And I'm going to do the typical test train split that we've always done. Okay, at this point in a normal random forest, based on what you have been doing, you would have probably used those loops that Jason showed you to optimize your random forest, to choose the best hyperparameters. I'm going to show you a different way to do that today. You don't have to know how to do this or even ever do this, but I'm going to show you this just in case you are interested. And this is a good opportunity to show you how to estimate hyperparameters in one fell swoop. Okay, so in Python, this is called grid search. In R, there's another thing that does this. It's called caret. And so basically what you do is you make a list for each of the hyperparameters that you care to optimize. And in this case, I'm going to try and optimize the number of trees in the forest, the number of features, and the number of samples that I'm going to split on. All right, I'm going to define a random forest here, and I'm going to only set the number of jobs, and I'm not going to set these other things, not quite yet. And then I'm going to instantiate this new object called a grid search CV. And a grid search CV is something that is built into scikit-learn. And what I'm going to put inside of this grid search CV is a random forest classifier, and then a dictionary of all the things I want to optimize on. And these are these three things. All right, so I'll run that code, and now I have this estimator instance, and what I'll do is I'm going to fit my training data, xtrain and ytrain, to that estimator. And what it's going to do is it's going to go through and try all of those parameters and use random forest out of bag score and try and figure out what the best model is. This is going to take just a few seconds because it's actually building quite a few random forests. Okay, and it's done. And so you see that it's done. There's a best estimator method, and I can go ahead and run that, or attribute, I'm sorry. And you can see that the best estimator is 400 trees, 7 minimum split, and let's see, the max features is square root. All right. So if I do best RFC equals estimator best estimator, what that does is that pulls out of all of the random forests that I built, it pulls out the best one. Okay. So I want to show you a few things about this model. The first thing is let's look at how accurate this model is. So to do that, I'm going to use the metric accuracy score. And accuracy is really pretty simple. What it is it's the number of correct answers overall in the model divided by the total number of answers, just like how accuracy on a test. You can see that the accuracy in this model is 97%, 97.14. All right, so that's pretty good. I want to just give you just a little bit more intuition on how accuracy works, just if there's any question. What I'm going to do is I'm going to make a variable here called y hat, and what that is the predictions of x test. We can print that, and we can see it's an array. These are the predicted values of x test. And then here are the actual values, 0, 0, 0, 1. And so all I'm going to do here is I built a little tiny loop, and it's going to iterate through the predicted values and true values, and it's going to increment correct when we get one right, and it won't if we don't get one right. And then at the end of the loop, we're going to take all the correct answers and we're going to divide by the total answers. You see that we get the exact same number as accuracy. Great. So that's accuracy. That's all accuracy is. Now the problem with accuracy is when you get into problems like the Titanic, where there's much more of one class than another class, it can accuracy isn't such a great metric because what we care to predict is survival, but survival rarely happens, and so a high accuracy score could just mean that we didn't identify anyone that survived and we just guessed that everyone died. Okay, so I'm going to talk a little bit in a second about why AUC is better than accuracy, and because it's not sensitive to that imbalance. But before I do, let's talk precision and recall. All right, so precision and recall. I'm going to run my classification report, and this is going to show me the precision and recall numbers for class 0 and class 1. So what I want to show here is the precision for class 1 is 0.96. I need to actually update this. This is for a previous run of the model. 0.96. Okay, good. And that means that there's a 4% chance. Okay, fine. And I'll update this one as well because we can see the recall is 0.96. Okay, very good. All right, so what precision is this is the ratio of type 1 errors, right? So the model is going to correctly identify 96% of the winners. Conversely, there's a 4% chance that it'll identify a non-winner as a winner. That's pretty good. Recall. So this is kind of the opposite thing. And this is of the people that the model said were winners, 96% of them are actually winners and 4% are not actually winners. So this is a type 2 error. 96%, probably great for when you're predicting who's going to win at billiards. It might not be acceptable when you're trying to figure out who's going to have cancer or not. So the precision and recall of a model and what's acceptable really depends on the domain and the space. And another thing that you should think about there is not only, well, maybe 0.96 is good, maybe it isn't. One thing that you could question to figure out or get some idea, feeling on if that's a good number is, what's the best current method? What's the best a human can do? What's the best current state? And so think about those things when you're evaluating those numbers. All right, I want to show you too the confusion matrix. And so this is kind of let's look at this and I'll explain what this is. If you imagine this is predicted 1, actual 1, so right here, this number is the number of true positives for class 1, which is people that we're predicting is going to win. So precision is, we go back here, I put the formula here for you, it's the true positives divided by the true positives and false positives. So a false positive would be someone that we said was class 1 but was not class 1, and that'd be this. So what we can do is to figure out precision, we can take 43, which is our trues, and divide it by our true positives and false positives, and we get 96%, which is exactly what we have here. Recall is very similar. What we do is we take the true positives and divide by true positives and false negatives, and that's true positives, false negatives. It happens to be the same, unfortunately. And this will get in 0.96. All right. So I know I've covered that before. I didn't spend a lot of time on it. Let's talk about AUC. So the AUC for this model is super good. It's 0.995. And I'll show you the rock curve again. And so AUC is not the same as accuracy. This is a common mistake in the homework. AUC really is a unit of measurement of area. And what AUC is it's this area here. All of this underneath this blue line, this curve. So this area is AUC, not the same as accuracy. The interpretation of this is that a AUC of 1 is a model that's perfect. It has perfect true positives and no false positives. And as this goes down, false positives increase, true positives decrease, and a point along this line is where we can use to set our threshold, which is the point that the classifier says, okay, at like 0.4, 0.5, I'm going to start saying it's a 1, not a 0, or maybe it's at 0.7 or 0.8. Regardless, so you can set a custom threshold using AUC, but more importantly, the most important thing to understand is the area under this curve here is the AUC, and it's the overall goodness of a model at any threshold. Okay, but here's the loop I'm about to throw you for. So far, our entire strategy for building models has been to fit a model as strongly as possible to that 20% holdout in the test train split, right? We chose all of our hyperparameters to make the very best model we could based on that 20% random sample. But what if that doesn't have all the tricky cases or the edge cases? Or what if that 20% sample is just not super representative of the rest of the model? Well, that happens a lot. And if that happens, what'll happen is that our model might not actually perform well in real life because it's going to be overfit to that exact specific training example. That exact test example. So what do we do to combat that? How do we handle this problem of overfitting to a very specific 20% holdout? Well, I'm going to take you through a simple method first, and that's just using a validation set. So what if instead we split our training set into 3 data sets now? So we take 60% of our data and we hold that off for training. And then we take 20% of our data and we use that for validation, which is model tuning, and then 20% for testing. So let me walk you through the workflow here. We take 60% of our data and we fit our model on that. And then we use a 20% sample that we call validation now, and we use that one for hyperparameter selection. So we use this one to build the very, very best random forest that we can possibly build. All right, now once we have that very best random forest, we can use this test set to measure how much are we overfitting, how well can this model generalize. And so this helps keep overfitting against our test set under control. But there's a downside, and that's our training set keeps getting it keeps getting smaller and smaller. So this is a good method when you have a very large N, but here we only have about 700 observations in our Bulliard's data set, and there was about 700 in the breast cancer data set as well. So let's talk about this other better option. And this is the option that we use most of the time in real life small model data science. And sometimes in big model too when we can afford the time. This is called KFold Crossvalidation. So here's how KFold Crossvalidation works. Let's say we have k is equal to 10. So we are going to have 10 chunks. We're going to split our data into 10 equal chunks. And then what we're going to do is we're going to train 10 models. And for each model, what we're going to do is we're going to take one of the chunks and put it aside for validation, for testing. And then we're going to take the other 9 chunks in the example of k equals 10 and use that for training the model. And then we're going to build a score. And then we're going to repeat that 10 times. So let me make sure that I'm clear, and I'll repeat that idea again. Take the data, split it into 10 chunks, build a model on chunks 1 through 9, test on chunk 10. Okay, then what we'll do is we'll iterate again, and we'll build a model on chunks 2 through 10, and we'll hold out 1. And then we'll repeat that process over and over again until every chunk has been used for testing and against the other 9 chunks. And so for each fold, we'll do that. And what we'll end up with is a result where we have k scores, right? So if we do this 10 times, we'll get 10 different scores back from the model. And that's what I'm about to do here. Now, notice when I'm fitting this, I'm fitting on the entire data set. I'm no longer fitting on a test because we don't need that test. The test is going to be done for us in KFold. I'm going to run that. Now the downside to cross-validation, KFold cross-validation, is that you have to build 10 random forest models. For 700 observations, that doesn't take very long. But for, hundreds of thousands or maybe millions of observations, that could take intolerably long. So in the big data space, the closer we get to big data, the less reasonable this approach becomes, the more we have to start doing something like the test train validation. The budget in big data becomes much more about time and less about correctness, or it has to be correct enough, but you have to be able to run it in the time that you have. Okay, so let's look at this. Scores is going to be a list of scores that came out of cross-validation. And here they are. And you can see that we have an array of scores, and they vary. So the first one, was these are AUC scores. 0.92, and this next one was 0.57 or 0.96, 0.97, 0.91, so that was a pretty bad one, 0.98, and look, we even have a 1 here. Some of you guys turned in a 1 AUC in the breast cancer exam in assignment, and that's what I saw was there was some pretty bad overfitting going on, and totally not your fault because I didn't tell you about this. You guys had no idea to do this. I didn't expect that we were going to have that easy of a time optimizing that model that we would actually end up with ones, but we did. So surprise. All right. So what do you do with this though? Because you have this range, right? This group of 10 scores. How do you move that back to a single score? Well, it's actually pretty easy. What you can do is you take the mean score, so the average, but of course, it's not quite that easy. So then what we need to do is we take this array and we compute the standard deviation, and then we compute the standard error. And if you remember from statistics class, that's the standard deviation divided by the square root of n, the number in your data set. And so what that's going to give us is about how much off each of these values is. So then what we can do is we can multiply that by 2.262, which is this is the value for 95% of, or in a two-tailed test, this would be a 95% student t distribution. And so then we can look here at the lower bound and upper bound, which are the mean score minus the confidence interval and the mean score plus the confidence interval. So I'm going to go ahead and run that, and you can see this is an actual score based on all of the AUCs that we ran through our cross-validation. This is probably the best, most accurate measure of this model's goodness. And you can see that we have a 0.968 plus or minus 0.018. And you can see I computed that. And so the interpretation of this is that there's a 95% probability that if this experiment were repeated over and over and over again, the average score would be between about 0.95 and about 0.98. Okay. So there's a lot of information there. Hopefully that covered up some of the questions that we had about validation, about overfitting, about accuracy and precision and recall and how they were different from AUC. If not, if you still have questions, please let me know, and we're going to do some homework on this as well. Thanks.